talked about the liquid electrolytes in batteries. Today I will move on. So this was the last slide from yesterday, in which we kind of figured out why we are using lithium hexafluorophosphate and EC, and with some linear carbonates in a particular ratio. We figured out why that happens, and all the additives that we can use for different functions, like BC for as a additive for both anode and cathode, FEC depending on the electrode we are using. These are all reactive additives. This is a co-solvent, and these two are basically our shut-off or shut-down additives that we use in batteries. Now then we move on to the solid-state electrolytes, in which the current state of affairs says, as I told you yesterday, the transpose number is much better in solid electrolyte, because you are basically fixing the anion lattice is fixed. It's a solid, right? So only mobile ion will be the cation, the lithium that we are talking about. So these are basically single ion conductors. So your lithium transpose number can reach close to 1. Now, what is good thing about this is, when you have a liquid electrolyte which has a very high conductivity value, but let's say half the transpose number, if you use a solid electrolyte which has a much lesser conductivity value, the total conductivity, but it has a very high transfer number for the ion which we are interested in, the cation. So that means even lower conductivities of ions in these materials would help. Another point you should know is, in solid state electrolytes, normally what happens is it serves the purpose of a separator and a lithium ion conductor. That means it will be electronically insulating, right? So you don't need a separator. Like in the case of lithium polymer batteries, what you do is, in polymer batteries you don't use a separator. You take a polymer, design a membrane out of it which is flexible, and you can work with it, and then you take our liquid electrolyte, organic solvent or inorganic salt, dissolve it in, and basically imbibe it in the membrane. So the polymer will act as a separator and as well as a conductor. That's a good thing with these. And there is also solid state polymer electrolyte, which basically is our, for example, polyethylene oxide, PEO, with some conducting agents in it, some lithium salt in the solid state. That is different from the lithium polymer battery that is commercialized. Lithium polymer battery that is commercialized uses the gel technology, that is membrane with our liquid organic solvent. That should be known. And here the case is again similar. The separator function is also there for solid electrolytes. And advantages compared to the liquid electrolytes would be a wider electrochemical stability window. Not only electrochemical stability window, but also chemically these solid electrolytes, if we are talking about, let's say, garnets and perovskites, means these are certain families of compounds which you use as solid electrolytes. Yeah, these things are very stable chemically against lithium, and also on the higher voltage side, on the cathode side. So if you use high voltage cathodes also, it is very stable against it. So that is one advantage. Another advantage is thermal stability, as I showed, is also chemical stability, and you take away the flammability and other aspects of it. Yeah, there is nothing to worry about the flash points, and also allows in redesigning new battery designs and all that. I say that because if you think of it, if you want to replace graphite as the anode material, and if you want more energy, the best I would say is go back to the lithium metal. I was discussing with some people in the morning that lithium metal might be the ultimate solution, because it's a wonderful metal. Yeah, you have the highest reduction potential and all that. Very good specific capacity and all that. And in that case, you want to use that, these solid state electrolyte, might prove a point, because if you want to use it against in an aqueous medium and all, leave the non-aqueous electrolyte, you can basically shield the lithium metal using this particular solid electrolyte and then proceed with the aqueous lithium cell. These kind of proposals are there. So that are another advantages that these solid electrolytes provide. And if you there is a ion conductivity and temperature plot, basically the Arrhenius equation follows, and you can see there is a comparison between all the solid state electrolytes and also the liquid ones seen here. So at the current state, there are certain compounds which has been reported like LGPS, LIG, that is lithium germanium phosphorus sulfide, which can attain this is inverse of temperature, 1000 by T. So your room temperature will be somewhere around here, 3.1 or 2. So at room temperature, already the solid electrolyte is showing conductivity similar to the liquid electrolyte. Yeah, that is around temperature minus 3 Siemens per centimeter, Siemens per centimeter. Yeah. So that is already there, achieved in solid electrolytes. The issues might be, there are different other issues, but we can do that. Yeah, in solid electrolytes can achieve that, certain families. So considering this LGPS and this is a garnet, I think, LLZTO and the perovskite, and this is the polymer organic salt thing that I told you about, the solid one. Yeah, polyethylene oxide and lithium perchlorate. And this is Lipon. Lipon is the other version, the gel electrolyte version. And so the whole idea is, solid is already approaching the liquid electrolyte conductivity. And here we have seen that how different potential energy is involved in liquid conductivity and solid state, because you have to, in a solid state, that would be the biggest issue about the diffusion of your cation, because there are periodic potentials, right, from one side to another. So it's not one flat activation energy you have to surpass, like in the liquid case. In the liquid case also you will have some activation barrier because of the ions that is traveling around, in the route which it takes, the attraction of the other anions. But here it will be even more, because every site has that other counter anion, the anion lattice is sitting there and will try to pull this cation. So whatever migration will be, every step is kind of periodic activation that is required. So conductivity, still we are able to achieve this kind of conductivity. Moving on, looking at this periodic table, you can see it shows, in blue it shows the mobile ions that has been investigated up to now in solid electrolytes. That includes lithium, sodium, potassium, hydrogen, copper, silver. Silver, one of the first material that was investigated heavily for conductivity was silver iodide. It shows all kind of properties. People have studied it like inside out. And copper ones, and oxygen also, oxide ion mobility in applications like solid oxide fuel cells have been used. And the green one, the red ones are the ligands, and the green ones and the red ones are the network forming elements. Yeah, network forming elements will have a transition metal, which is shown in green, mainly transition metals, and even sometimes rare earths. And the red ones are the ligands which will form the whole polyhedral network. And the point we have to make here is, if you observe this, I have told you this has a separator function. The electronic conductivity should be much less. Yesterday Professor Vedi Madhav was talking about the speciality of 3D orbitals. When electrons sit inside 3D orbitals, they reside much closer to the nucleus than outside. That means it is more localized than itinerary. He was talking about that, if you remember correctly. The same way, if you see most of the solid state electrolytes, you will see transition metals in the first row. That is 3D metals. Yeah, titanium. Transition metal first row means, I'm a chemist, so I assume that everyone knows transition metals and everything. But what it means is this row. 3D means this row. Yeah. So you will familiarly find more transition metal from that to provide that particular function of low electronic conductivity, because electrons are localized, it's not itinerant. Yeah, that's the reason why whichever solid electron, for example, in the previous slide, you see there will be a zirconium, lanthanum, titanium, and all sitting there for sure. Rather for different reasons, but titanium, vanadium, and all kind of 3D elements. And another point I would like to make is the valency and the ionic size, yeah, of the mobile ion, how critical it is for the diffusion coefficient. So they have done some studies in if you take lithium sulfate and it's comparable substituting with other ions, the alkali metals, with the same valency, and also metals with higher valencies. Yeah? They compare that. The basic observation is that the monovalent ions will have the highest diffusion coefficient and the lowest activation energy. And not only the valency but the ionic size will also influence your conductivity. Here you can see it is not a straight linear relation here. You can see there is an optimum size of an ion which will make it more mobile in certain crystal structures. In certain crystal structures, it has a fixed crystal structure. That's why you get this peak here. Lithium ion is too small, so that what happens is it can get into some comfortable, deep potential well minima, and it's comfortable there with the surrounding anions. So you require more activation energy to push it out. Yeah, and bigger ions definitely will feel more drag because of the surrounding anions that are sitting in the lattice. So these two factors make this peak that is possible. So there is an optimum ionic size where ion can really reach through the material. That is the point. And this is the activation energy and this is the diffusion coefficient. They are related very close. So that's the whole point. This is the optimum ionic size for this one. Yeah, just to give you an overview of the structures that is involved in here. And one kind of materials are called silicon-like structures. So the basic structure is something called gamma lithium phosphate. Yeah, and of course your mobile ion is lithium. And there are structures called nasicon. This you might be more familiar with this because it's a superion conductor which is used for even in the fuel cells or solid oxide fuel cells. And garnets are of course there. Ab2O4, general formula Ab2O4 garnets, which also form different polyhedral networks. So normally it's the transition metal and the other ligand which form the polyhedral network and lithium getting distributed in the channels or depending on the need. The basic idea of these formulas we have already seen yesterday itself. You need a diffusion coefficient, the Nernst-Einstein equation which talks about mobility and diffusion coefficient, and the lithium-ion conductivity which needs activation barrier. Now, the point we will discuss in this slide is the optimum amount of ionic species concentration for maximum conductivity. Yeah. So every basically if you start doping or creating defects, yeah, in a material in order to increase the mobility of the ion, there is always you find optimum critical concentration where it is going to conduct ionic conductivity to the maximum. Yeah, whether it is lithium ions or even in certain systems which contain oxygen mobility, there will be an optimum you find. And why that happens is because the lattice distortion causes increase in migration energy or decrease in extrinsic effect. Yeah, when you try to dope, you are basically playing out with the structure. So small changes in the structure will produce certain distortions in the polyhedra, which will basically push the activation energy. So that will cause the decrease in ionic conductivity if you dope beyond that critical concentration. Before that, structurally it is not effective, yeah, or not effective enough to create a change in the ionic conductivity. But after that, it will bring down. So you can see after this value of critical concentration in this particular compound. So you can actually calculate the optimum amount of defects and the mobile ion concentration required for a solid electrolyte. That you can figure out. That's the point. Then this table will show you the current state of affairs of solid state electrolyte. With this is thiolisicon family Li10 MP. M stands for silicon, germanium or tin, then phosphorus and sulfur. This compound is recently reported as supposed to be very, very highly anti-conducting for a solid state material. And there are families, lysicon, ergorodite, these are all inorganic families, garnets, nasicon, and so on. So mainly people are working on these three materials and also on perovskites because of this ease of synthesis and easy to work with, yeah, perovskites, oxides, so, and also the stability it offers and all that. And what people try to do here is, they try to normalize the ionic conductivity because different compounds are having different amount of lithium in the structures, right? And certain structures, all the lithium may not be mobile in all the structures. So we have to normalize the mobile lithium in the structure. So what they do is they normalize the ionic conductivity just by dividing the amount of lithium found in the unit cell and the charge it's carrying. And then also they get similar profiles, except for the fact that now the difference between garnets, perovskites and these things have come down. Yeah, that basically means it can carry, the perovskites can carry, have similar ionic mobility. So although it may not be highly conducting, but if you consider the mobility in these materials, then everything will fall into the same category. And in garnets, there is definitely a higher amount of lithium, but it is not as mobile as the other family. That's why you get lesser conductivity when you normalize the conductivities. And take home message, what I made in this also electrolyte is like, this lysicon type material or thiolysicon as they are called, because they all contain sulfur as an anion in the structure. Now there should be a reason why people are putting sulfur there, right? I mean, it can't be accidental. A lot of people think that experimental physicists, experimental chemists, basically, like Tanmay was saying, like we work with very funny stoichiometries, 1.34, 4.1. It's not very accidental. There is some planning and all behind that. There's a reason for that. So same way, putting sulfur in the anion structure, what it makes is, it is one issue with sulfur is that it's volatile and water sensitive. That's the reason why these high conducting things can't be used currently in the materials. They have stability issues and they're very synthesis of sulfur compounds. If you people have done any of that, you will know it's extremely difficult to hit a particular stoichiometry because of the volatility of sulfur. So there is a lot of trial and error involved and optimization often is difficult. That's what the main point, the negative point, and it's also water sensitive, hygroscopic, heavily hygroscopic. So you need the inert atmospheres of walls and everything. Then why this happens is when the sulfur, they did a study to understand this. When sulfur is below oxygen in the periodic table, yeah, you are coming down the group, yeah, oxygen to sulfur. Same way they started, they took one lithium halides, one family of compound. Yeah, really.
Sir, I want to know from the previous slide. I want to know how we are justifying that particular structure is having good ionic conductivity or not. How we are justifying that this particular.
I'm not justifying anything. I'm just telling you it's an overview. Whatever compound is being synthesized in solid state electrolytes, these are the families which are those found. Yeah, and one reason why, like in the lysicon type material, sulfur is one of the reasons why you are getting this high conductivity. And the reason I am going to say here is when you check out these lithium halides here, and the halides, the radius is increasing down the group. When you come from fluorine up to iodine, and they have found out that the electronegativity is definitely decreasing, the ion size is increasing. That basically means the polarizability is also increasing. So they can basically manage the negative charge better than the oxide ion. And that they say is very important in this anion stability of these structures. And that includes thiolysicon. Yeah, thiolysicon just means you have sulfur in there. That is increasing lattice volume by substitution, larger bottleneck sizes and thus ionic conductivities. Now bottlenecks in solid state diffusion basically means all the drag and the electrostatic attraction an ion can feel when it is moving. Yeah. Structurally also, let's say earlier in the earlier talk, we talked about lithium iron phosphate having a one-dimensional diffusion. Yeah, spinel having a three-dimensional lithium diffusion. So normally in a battery case, we would like to have a three-dimensional diffusion. That would be perfect for us. But in lithium iron phosphate, you don't get that. Yeah, you get the way lithium is distributed in the layers, you get movement along one particular direction. Lithium diffuse in that direction. Yeah. So in that case, more than the structure, the morphology becomes very important. Where the lithium moves, in which direction. In the spinal case, it doesn't matter, it can move in all three. Yeah, that's why in LFP, the ionic conductivity is so low unless you do the tailoring of the phase. Let's say you make a particular phase so small in which that ion is supposed to conduct, you get faster conductivity. That's why how morphology becoming important in ionic conductivity. And then Nasicon and perovskite type have stability issues with lithium metal. It is very easy to test. In a glove box, you just melt, keep a hot plate, melt lithium, throw the compound in, make a pellet of Nasicon or something, put it in and then check it out after some time. Leave it for some hours. You need a lot of glove boxes, but you can still do that. All this off the beat experiment should be done in a separate glove box. Can't be that lithium battery is assembled in the same glove box as this, where this is tested. You have to be careful. So, but yeah, you can test it out very easily, chemically and electrochemically as well, if you will decide. So, especially when high oxidation number transition metal is present, it will not be stable with positive ions. Yesterday also, positive electrode. Yesterday also we saw that. Whenever that transition metal can come down to a lower, let's say it shows a lot of oxidation states available for the transition metal. It will prefer when it can ion exchange with hydrogen or something to come down to a lower oxidation state. Yeah, that is possible in when the positive electrode will provide. That's why it becomes a bit unstable. So all the, like we saw for the electrolytes also, right? Cl7 plus in perchlorate and P5 plus in PF6 and all. And garnet say look the most promising among them because of the chemical stability and the ease of synthesis. I mean, relatively, garnets also not very easy to synthesize. I will tell you, I worked on garnets for some time, LLZTO and all that. There was a report in Nature when they first reported a garnet LLZTO. They showed very high conductivity values, and later they realized that they used to synthesize it in an alumina crucible. Yeah? Later they realized that Al3 plus is actually getting into the structure and stabilizing a particular structure. They thought, go to know the later research revealed that. So it's not very easy because then you have to be careful with the material, crucible material you use and all that. Yeah? So whenever someone is working on garnet, avoid alumina crucibles. Or do an alumina crucible. If you are not getting results, do it in an alumina crucible. If you are getting results, yeah, then fine. We can check out inert platinum crucibles and all. So then I come to separators. Here I never worked with these separators in my lab. I have no personal experience because normally in lab we use glass fibers. That's the easiest way. Instead of all these commercial available cell guard separators, we normally use glass fibers. But we need cell guard or these kind of polymer separators in applications commercially because we have to check out a lot of safety issues, right? I mean, dendrite growth and all that has to be prevented. Glass fibers may not be the best option. So main function is to keep the positive and negative electrodes apart to prevent electrical short circuits and allow rapid transport of ions. That's the main idea. Requirements. Electronic insulator, yeah, very clear. Minimum electrode resistance ions should pass through. Mechanical and dimensional stability. And what is the, readily wetted by electrolyte. That is a very important point. People who work with lithium ion battery, if they have used cell guard separator with EC and other common solvent separator will know that some salt and solvent combination doesn't wet the separator well. You have to figure it out yourself before just taking the cell guard and making the battery or the cell. Yeah, you have to check it out. So normally we all start with glass fibers, that's the easiest option. But then the glass fibers have a trick. because glass fiber is not very pure. Someone was talking about doing XPS studies on the decomposed products or something. The guy is missing now. No, he's there. Yeah. So in that cases, if you are trying to use a glass fiber separator, because glass fiber separator has a lot of metal impurities, including nickel, including copper. Yeah. So you have to be careful with that. Yeah, to be very, when you are trying to do very precise studies of what is getting deposited where not, be careful about all separator that you use and all that. Yeah, it will be good. And these are the commercial separators available for lithium-ion batteries. Yeah, there are a lot of other lithium-ion.
During the path, how they will be separated between the separator and the cathode.
Yeah.
The separator, we are keeping it away from between the positive and negative charge.
Yeah.
But in the between the there will be these are not there will be some distance between the separator and the anode and the separator.
No. They are all compressed together. No.
They are all compressed. No, there.
Why should there be? But actually, your electrolyte is sitting inside the soak, no, in the separator. So this is the commercial one. So liquid electrolyte will have a microporous pore size with polyolefins. They normally use polyolefins. So they are polyethylene, polypropylene, or a tri-layer separator. Celgard makes that called which will have PP and there's a reason why they do that. I'll tell you. And the lithium-ion gel polymer can even use PVDF and polyolefins coated with PVDF or other gelling agents. And lithium polymer, the solid state one, uses polyethylene oxide with the lithium salt. And the standard pore sizes is around 0.03 to 0.1. Porosity is very important, as there was because someone was speaking in the morning, porosity of electrodes. So porosity of separators are even more important to soak the electrolyte into it. And thickness of less than 30 micrometers. These are all standard commercial separator values. This property is what they use basically to the melting point of separators, polymers, is how they shut it down. When there is the temperature increases more than 135, you can shut down the battery using this melting technique. Yeah, it will become the porosity of the polymer is gone. It loses the porosity. That means no more lines can move in, and there will be immediate shut off of the battery. So polyethylene melts at a lower temperature than polypropylene. Yeah, and polypropylene is more mechanically strong because of the higher melting point. That's why they use this tri-layer concept in PP, polypropylene providing the mechanical integrity and PE providing the shutdown properties of the polymer. And this is the same images of the Celgard commercially available separator look like. Now this is our cross-sectional one, it's a cross-sectional view of the tri-layer separator, polypropylene, and polyethylene. Yeah? And this is the surface SEM. And these are the varieties of separators that are available, and from single layers to tri-layers. And the figures here, you have to worry about is given here. For a separator, when you choose a separator, what should you worry about? Yeah? Thickness, girly, anisocity, porosity, and melting temperature. I'll talk about a few of them in detail. Like thickness. For consumer applications, preferably you should have less than 25 micrometers. For EV application, you should have a thicker separator because your battery pack is bigger, so it's better to be safer with the graphite core. It also gives better mechanical strength and less puncture during fabrication. Fabrication in the sense when you play around with the separator in making a assembly. Now, thinner, it is better if you have a low resistance and less space and increase in diffusion area. So, you're basically trying to make it thinner and thinner. That's why whenever you get a chance of using a thinner separator, you do that as in normal consumer mobile application. Permeability is a factor. So when you put the electrolyte into the separator, they say that the effective resistivity of the electrolyte goes up by a factor of 6 or 7. Because now the separator is also contributing. Now there is a Macmillan number which is defined, which is nothing but resistivity of the separator with the electrolyte, with the resistivity of the electrolyte alone. That basically defines the property of the separator. Now normally a Macmillan number of 10 to 12 is agreeable or is a standard for a consumer cell. You don't have to click it. I mean, you will get a PowerPoint. You are participating. Tortuosity. Yeah, this was also taught by Professor Vikas Kumar in the morning. He was talking about the tortuosity of the electrodes again. What it means is it's a mean effective capillary length to the separator thickness. So basically, how effectively the electrolyte is seeped in to the separator. That's what it means. Tortuosity factor tau is defined as length, that is ion path through the separator by the thickness of the separator. And ideally, if you have a perfect separator, the ideal it will be the tau, if it is 1, the tortuosity factor will have an ideal cylindrical and parallel pores standing right through the separator. So that will be the ideal case, which you never get basically. So any tau value of about close to 0.75 is considered to be quite good in the case of consumer. And there is another parameter, it's called a Gurley. Gurley is basically an air permeability check. So they do it by time of specific amount of air to pass through a specific area using under a specific pressure. That is how that term is defined. So lower Gurley values you will have a better. That means you have high porosity and low tortuosity. That's what you look out in that Gurley. These are all industrial technical definitions. Yeah. But if someone wants to work in separators, you will very well know this as well. So wettability and wetting speed. How good they absorb and retain electrolyte, and also the wetting speed is directly correlated with the electrolyte filling time. That is very important. You know, whenever you make not at the lab scale cells, like when you do it with micropipette or something, it doesn't matter. Anyway, you can throw in a more electrolyte in there, nothing's going to happen. But when you make commercial cells, when you are doing it using machinized or semi-automatic way, the filling time is very important, because that has to basically soak the separator. Although you give some time, normally when you fill the electrolyte into the prismatic cells, you give some time for the electrolyte to soak out. But this filling time is also pretty crucial in the wetting speed. So hydrophobic separator, that is, as I told, in cases where the separator doesn't get wetted by the electrolyte, you can use some wetting agent to improve their wetting abilities. That can be done even in lab as well. When you work, you see that your cell guard is not absorbing enough electrolyte. There are ways to counter that. By the way, so there are one of the few hydrophobic things that stand inside the battery. One of them is a separator. Graphite is the other one. But the other side, cathode is our problem side, which is hydrophilic, just for information, right? Because even LFP that we work with, that is quite hygroscopic. If you check the literature, there are results in which water is absorbed if you just leave LFP for an atmosphere for a long time. Why it is detrimental? Because we are talking about our electrolyte LiPF6, which is going to be attacked by any amount of water in it. Yeah, immediately creating hydrofluoric acid. Corrosive, your cycle stability will fall down like seconds, like 10 cycles, it's gone. So that is why water content is very important. That's why this is kind of a help for us. At least on the anode side and the separator we don't worry about. We worry only about the cathode and the electrolyte. So if you maintain good standards in that, then you can get over. And there is something called shutdown property. So this is what they show in the resistance, and as the temperature increases to the melting point of, let's say, this tri-layer, the polyethylene thing will melt. Yeah, there's an immediate increase in the resistance. So they use it as a gauge basically to shut down the cell. Yeah, and the shutdown ability is basically depending on the molecular weight and percentage of crystallinity of the polymer. And tri-layer cell guard separator is the best for any commercial, especially application use. And these things you will anyway get the slides, you can go through. These are the basic cell property, separator property, and the comments that you can think of. Like, for example, one interesting would be It's not very interesting. Anyway, yeah, overcharge and shutdown protection might be one of the important points. You can read about this when you get the slides. So with that, yeah, thanks. Thanks for your attention. Yeah, one second.
This core styles,
Yeah.
I mean, how does it play the role actually? I mean, you can see is depending on the porosity, basically the wind, there will be an effective window basically. I mean,
Yeah.
how the lithium is going to move from here to here.
Yeah.
But does it affect the intrinsic conductivity of the electrolyte, the size, the core size? And what I mean is, suppose, I mean, this whole room is like a core, okay? You have the liquid here. So basically the ionic conductivity here doesn't get affected by the
You're saying it is just a physical barrier rather than a
physical
chemical
barrier, or also it, in some way,
Yeah.
this has an influence on the air.
It should be, or else they can't demand to have a porosity of 40 to 50% on the separator, right? It can't be to stop the lithium dendrite growth. No,
Right.
that is the thickness of the separator. So
Right.
porosity plays a role, I'm sure, but how? Not very sure. It should be a physical effect more, right? I mean,
Not just a physical effect, that's
Effect.
what I also
Yeah, I think so.
Yeah, it will reduce the conductivity. I mean,
for sure.
because
The mobility reduces
mobility
means, yeah,
reduces because the effective area is coming down.
exactly. Should be the case.
So,
Yeah, someone.
One electrolyte and constant electrolyte who have ionic conductivity high. What temperature they have?
That first slide, no? That I showed. This one, no? This one. Yeah? This is 1 by T, right? 1000 by T. It is temperature and ionic conductivity is floated. So your room temperature will be around 3 point something, right? This is the room temperature. So if you go in this direction, your temperature is
yeah, please come back. Just
Decrease.
go outside, but please come back.
Okay, low temperatures are they tested at around -30, -40 degrees centigrade? This is the ionic conductivity.
I don't think more beyond -20 they will never do that, but it is important. But at least in this particular salt electrolyte case, they won't. Because anyway at the room temperature you are not catching, it's just catching up with the liquid electrolyte. That will be more important in the case of liquid electrolyte, right? Definitely it will be lesser than liquid electrolyte.